let's think about what might happen if we had a solution of this molecule and water and how they might react. And just as a bit of review on naming, let's just name this molecule. The longest chain, let's see, we have 1, 2, 3 carbons. So it is going to be a prop. It's an alkane, all single bonds. So it's going to be propane. Propane. And then this is our longest chain right here. 1, 2, 3. We have this methyl group off of the number 2 carbon. And we also have the bromo group off of the number 2 carbon. So it's going to be 2 bromo. Let me write this here. It's going to be 2 bromo, 2 methyl, 2 methyl. Let me write that a little bit neater. So it will be, I'll need more space to the left. This is going to be 2 bromo, 2 methyl, 2 methyl for this methyl group off the number 2 carbon, propane. So let's think about how it might react with just water. Now, in this example, water is going to be our nucleophile. It has some electrons already over there, but even more, it's very electronegative, which we've seen multiple times. So it's hogging electrons from the hydrogen. It's not as strong of a nucleophile as the hydroxide anion that we saw in the Sn2 reaction, but it is a nucleophile. This is actually a weak nucleophile. This right here is a weak. This is right here is a weak nucleophile. It wouldn't mind maybe being attracted to a nucleus because it has extra negative charge. It has a partial negative charge on this side of the oxygen because it's hogging hydrogen's electrons. You have partial positive charges on these sides. But it's not as strong as a hydroxide, which has an actual negative charge, not just a partial negative charge, and really wants to offload electrons or is attracted to a nucleus. So this is a weak nucleo. We have a weak nucleophile. We're going to talk more about, we're going to see one type of reaction in this video, and we're going to talk more in several videos about when this type of reaction versus an Sn2 type of reaction might occur. So let's look at this right here. We have a bromine right over here. We know that bromine is very electronegative and that it is somewhat stable. It's somewhat stable when it has a negative charge. At least its valence, it'll have 8 valence electrons, which makes it feel relatively good, although charge is never a super stable situation. So maybe, and I'm not going to say that this is, well, this is that the reaction will go, super fast in this direction, but maybe bromine will take away the electron that it has from carbon. It was already hogging it a little bit, right? It is already more electronegative. Let me draw all of bromine's valence electrons. So it has that 1 that's on that side with the carbon. Let me draw the carbon electron on the other side of that bond. And then it has, that's 1, and then it has 6 other valence electrons. So 1, 2, 3, 4, 5, 6, 7 total valence electrons. So maybe we can imagine a situation where bromine takes this carbon's electron all together. So let's draw that out. So it literally will take this electron all together. So it will take that electron all together. And once again, I said this isn't going to be, the super fast direction, but it could happen. It could happen. And so this reaction won't necessarily, go super fast. We'll kind of show it'll be in equilibrium. So if that were to happen, we'd be in equilibrium with this situation. So let me draw my original. So I have my carbon. I have that CH3 group behind it. I have the CH3 group in front of it. I have the CH3 above it. But now the bromine has left. The bromine has left. It's no longer bonded, and it has its original 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. This one right here was originally bonded with an electron from a carbon, but now the bromine has taken that orange electron altogether. So now bromine has taken that orange electron altogether. It has a negative charge. The carbon has lost that orange electron, and so it has a positive charge. Now, it could be interesting if oxygen comes into the mix. Because now, if oxygen comes into the mix, if water comes into the mix, so let me draw the water molecule right here. The water molecule right over here. It is a weak nucleophile, but this guy really wants an electron. He has a positive charge. It is a tertiary carbocation, so it's reasonably stable. That's actually one of the reasons why this can even happen. If this was a primary, or if this was just if it was connected to no other carbons, then it would be very hard for this thing to just return into a carbocation. But because it's tertiary, it's somewhat stable, but it doesn't like to have that positive charge. It really wants an electron. So you could now imagine that this oxygen, or sorry, this water, I have to be careful, this water will give one of its electrons. So maybe that electron right there will be given to the carbon. This, I guess you could view it as this is the nucleophile, and it's being attracted to the carbon's positive nucleus. So then what will happen? And once you're in this state, this reaction actually will occur much faster than this one right here. This is actually a reasonably stable situation. That's why I drew the equilibrium. But now this will actually be a faster reaction. So I'll just draw an arrow here. So I'll just draw an arrow here. And then it will look like this. So we have our original carbon, the original molecule, that's the thing that's behind it, CH3. We have another CH3 in front of it, CH3 in front of it. And now this water is attached to it. So let me draw the oxygen and the two hydrogens. Oxygen had these two electrons. It had another electron here. That's that one right over there. Let me do it in this color. So this has this electron here. But its pair, the thing that it was in a pair with, is now given to the carbon. And they will be bonded. And they will be bonded now. These two guys are still paired up. Now, since oxygen, this water had a neutral charge, but now it's given away one of its electrons. So now the water itself will have a positive charge. Or I guess this water group, or you can kind of say it's kind of an oxonium group now. It has a positive charge. And so the last thing that might happen is maybe another water molecule, or actually it could even be the bromine, comes along and grabs one of the hydrogen protons, and so that this electron can be taken back by this oxygen. Let me show you what I'm talking about. So maybe you could imagine another water molecule. There's gazillions of them. Let me draw another water molecule here. We have another water molecule right here. Might go, and this would happen simultaneously. This might give one of his electrons to, say, that hydrogen right there. And if that happens, simultaneously, this electron that this hydrogen had could be given back to this oxygen right here. So that oxygen will take back that electron. And when that reaction happens, we will be left with, let me draw our original structure. So we have the CH3 behind us. We have the CH3 in front of us. We have the CH3 above this carbon that's doing all the reacting. And then it is bonded to an oxygen, which is bonded to a hydrogen, to only this hydrogen, because it took back the electron from that hydrogen right there. Just like that, you also have the bromine with its negative charge, and it has 8 valence electrons now. And then, of course, you have an extra oxonium. So this oxygen right here gave this electron to this hydrogen. So now it will be bonded. It will be bonded to that hydrogen. And if you wanted to draw all of the valence electrons on this oxygen right here, it would look like this. So you have these two. So 1, 2. You have the one with that 3 that's bonded with that carbon. Let me do that in a different color. So you have this one is the same thing as that valence electron. It has the one bonded with the hydrogen. Actually, let me make the bond clear. It has a bond here with the hydrogen. So that's this hydrogen bond right here. This bond with the hydrogen. I don't want to call it a hydrogen bond. Well, I think you get the idea. It has that valence electron right there on that end of the bond. And then it had this valence electron. It had this one right here at this end of this bond with hydrogen. That was just like that. And then it took the other electron from the hydrogen. It took the other electron, and so it's right there. So once again, it still has 6 valence electrons. It is now a neutral oxygen. 1, 2, 3, 4, 5, 6. So we were able to react this 2-bromo, 2-methyl propane with water, which is a weak nucleophile. We'll talk more about strong and weak nucleophiles. And we got to, what is this thing right over here? Well, it's still our longest chain is 1, 2, 3. It's still prop. We're going to have prop as a prefix. And I actually haven't taught you this. But since we have an OH group, over here, this is an alcohol. Alcohol. And the way you name alcohols is you finish, the suffix is anol. So we would call this is propan. And sometimes I'll just say propanol. But since we want to specify which carbon we're on, this is the 1, 2, 3 carbon. This is propan-2-ol. Propan-2-ol. And of course, we also have a methyl group on the 2 carbon. So it's 2 methyl propan-2-ol. Now, this whole reaction that I just showed you is called an Sn1 reaction. And you might have a gut sense of why it's Sn1 instead of Sn2. So let me write it down. It's Sn1 reaction. The S still stands for substitution. It still stands for substitution. The N still stands for nucleophilic. Nucleophilic. Right? We had a weak nucleophile in the water molecule, so it substituted. Now the 1 stands for the fact that the slowest, the rate determining step in this mechanism, the one that is going to happen the slowest, that only involves one of the reactants. This right here was the rate determining step. The bromine taking the electron away from the carbon. It did not involve this water at all. It did not involve both the reactants like we saw in the Sn2 reaction. Since it only involves this one reactant, it is an Sn1 reaction.